Assalamualaikum to our beloved lecturer, Madam Atika binti Razi. I am Muhammad Aiman bin Malik from Group 1. My teammates are Muhammad Zaid bin Abdul Jabbar, Muhammad Ammar bin Samsudin, and Muhammad Alif Haziq bin Adnan. We are going to present about field effect transistor, FET.
Assalamualaikum warahmatullahi wabarakatuh. Today I will present about FET. There are many types of FET, which is JFET and MOSFET. JFET divided by 2, which is P channel and N channel. MOSFET divided by 2, which is the MOSFET and E MOSFET. These are the construction of JFET. N-channel is made from N-type material for major part of the structure and embedded layers of P-type materials. Vice versa with P-channel, but N-channel is more widely used. The terminals are source, gate, and drain. The depletion region at each junction shows that resembles at same region of a diode under no bias conditions. Recalls also that a depletion region is void of free carriers and is therefore unable to support conductions. Construction of MOSFET. MOSFET have characteristics similar to JFET and additional characteristics that make them very useful. The metal oxide semiconductor field effect transistor MOSFET is the second category of FET. The main difference is that there is no actual P-N junction as the P and N materials are insulated from each other. Gate region is physically isolated, eliminating the possibility of the current even forward bias. Most FET are static sensitive devices and must be handled by appropriate means. The MOSFET is divided by 2, which is the MOSFET known as depletion MOSFET and E-MOSFET, which is enhancement MOSFET. E-MOSFET has no structured channel as the picture in my slides. Let's go to play.
Assalamualaikum and hi. So now we'll continue on the symbols of FET. So as we learned before, which is the BJT, we have collector, emitter and also the base. But on the FET we have drain, D, gate, G and also source, which is the S. On the symbols also, we can determine the electric field by seeing the arrow direction. Not only that, as we have two different types of FET, they can be either N channel or P channel. On this slide, we are working of FET. In here, the currents are flowing from source to drain. Second, the FET are called voltage control devices. It is because the current in drain, symbolized as ID, depends on the voltage across the gate. There are two events that influence it. One is depletion channel and the other one is enhanced. On this slide, since the JFET is operated in reverse biasing, it has an assembly input impedance. The current in JFET for gate is 0. The input voltage, which is represented by VGS, is the controlling factor for the output current, which is represented by ID. So the last slide for working JFET, when there is no voltage across gate and source, the channel becomes a smooth path which is wide open for electrons to flow. Second, the reverse thing happens when a voltage is applied between gate and source in reverse polarity. That makes the PN junction reverse bias and makes the channel narrow by increasing the depletion layer and could put the JFET in cut-off or pinch-off region. In the below image, we can see the saturation mode and pinch-off mode, and we'll be able to understand in the depletion layer become wider and the current flow become less.
The characteristic of JFET Crofts part. First condition, VGS equals to 0, VDS increasing to some positive value. In this case, the N-type channel will simply behave as the resistance region. The flow of current from drain to source will create the voltage drop between the gate and source. This will eventually result in reverse biasing of the gate source terminal. The reverse biasing will be more towards drain region than source region. There are 5 parts in the graphs that we should know. First of all is knee point. Knee point. There exists a point in the characteristic curve where the variation of drain current with drain source voltage appears to be linear. But after this point, the linearity changes into a curve. The second part is channel ohmic region. The region to the left of the knee point in the characteristic curve is the channel ohmic region. The third part is pinch-off point. Pinch-off point is the point where in the curve above which the drain current does not increases no matter how much we are increasing the drain to source voltage. This point is termed as the pinch-off point. The fourth part is pinch-off voltage. The voltage at a pinch-off point is termed as pinch-off voltage because at this voltage the current is completely turned to be constant. Drain source saturation current is the last part of the graph. The drain to source saturation current is the current which becomes constant or completely enters a saturation state. The region after the pinch-off point in the curve is termed as saturation region. When the JFET is allowed to work as an amplification device, the JFET utilizes this region for operation. The characteristic of JFET graph spot. Second condition, VGS values is lower than 0, VDS at some positive values. As VGS becomes more negative, the JFET experiences pinch-off at a lower voltage. ID increases even when VDS increases. ID eventually drops to 0 ampere. The value of a VGS that causes this to occur is designated VGS is off. Note that when VDS reaches at highest level, JFET experiences breakdown situation. Thus, ID increases uncontrollably when VDS value is higher than VDS value maximum value. The JFET is likely destroyed.
Assalamualaikum and hi. My name is Muhammad Fazik and today I'm gonna tell you about graph operating condition to JFET. Voltage control resistor. The region to the left of the pinch-off point is called the ohmic region. The JFET can be used as a variable resistor where VGS controls the drain source resistance RD. As VGS becomes more negative, the resistance RD increases. Voltage control resistor VCR may be defined as a 3-terminal variable resistor where the resistance value between two of the terminals is controlled by a voltage potential applied to the third. For a junction field effect resistor JFET, under certain operating conditions, the resistance of the drain source channel is a function of the gate source voltage alone, and the JFET will behave as an almost pure ohmic resistor. Maximum drain source current IDSS and minimum resistance RDS on will exist when the gate source voltage is equal to 0 volts. If the gate voltage is increased negatively for N-channel JFET and positively for P-channel, the resistance will also increase. When the drain current is reduced to a point where the FET is no longer conductive, the maximum resistance is reached. The voltage at this point is referred to as the pinch-off or cut-off voltage and is symbolized by VGS equal to VGS off. Thus, the device functions as a voltage control resistor. JFET P-channel. P-channel acts the same as the N-channel JFET except the polarities and currents are reversed. And P-channel JFET turns on by taking a positive voltage to the source terminal of the transistor and a gate source voltage VGS between 0 volts and 4 volts. It shuts off by taking in a positive gate source voltage VGS above 4 volts. The main point is that a P-channel JFET turns on by applying a positive voltage to the transistor source terminal and ideally no voltage to the gate terminal. The transistor circuit shuts down when it detects a positive gate voltage VGS greater than about 4 volts. When the voltage at the gate terminal is 0 volt, the transistor is fully conductive and operating at maximum capacity. The transistor becomes less conductive as the amount of positive voltage applied to the gate terminal increases. When the positive voltage reaches a certain level, the p-channel JFET circuit ceases to conduct across the source drain terminal. The characteristic of the p-channel. As VGS increases more positively, the depletion zone increases. ID decreases. Eventually, ID equal to 0 ampere. Also note that at high level of VDS, the JFET reaches a breakdown situation. ID increases uncontrollably if VDS over VDS max. Here we have a cut-off region, off-mid region, saturation region, and breakdown region. Cut-off region is the region where the JFET transistor is off, meaning no drain current. ID flows to the source drain region. Off-mid region is a region where the JFET transistor begins to show some resistance to the drain current ID that is beginning to flow to the source drain region. This is the only region in the curve where the response is linear. Saturation region is the region where the JFET transistor is fully operational and maximum current is flowing. During this region, the JFET is on and active. And breakdown region is a region where the voltage that is supplied to the source terminal of the transistor exceeds the necessary maximum. At this point, the JFET loses its ability to resist current because too much voltage is applied across its source drain terminals. The transistor breaks down and current flows from source to drain. The transfer characteristic of JFET. The transfer characteristic can be determined by holding the drain source voltage VDS constant while changing the gate source voltage. As a result, increasing the gate source voltage VGS in the negative region causes the drain current ID to decrease. The transfer characteristic of input to output is not as straightforward in a JFET as it was in a BJT. In a BJT, indicated the relationship between IB input and IC output. In a JFET, the relationship of VGS input and ID output is a little more complicated. By keeping the drain to source voltage at pitch of voltage, the transfer characteristic is drawn between gate voltage and drain current. The maximum drain current flowing to the transistor when the gate is at zero potential is known as shorted gate drain current, IDSS. As the gate negative potential increases, the corresponding drain current decreases. The drain current becomes zero after a certain negative gate voltage. The gate to source cut-off voltage VGS is the negative gate terminal voltage at which drain current becomes zero for the applied drain to source voltage, which is the same as the pinch-off voltage.
Junction gate field effect transistor JFET. Example: determine the value of drain current for the circuit shown in figure 3. To solve this problem, first we have to extract the data from the figure 3. Figure 3 has given us the cut-off voltage, which is -6 volt. The maximum current for this device is 3 milliamps and voltage from gate to source, which is 2 volt. After that, we can use the formula to find the drain current, which is drain current equals to maximum current in the device multiplied with square of 1 minus voltage of gate to source divided by the cut-off voltage. So the answer is the drain current of this JFET is 1.33 milliamps.